Rahim. Good evening, guys. Today we'll try to solve an example related with how we can calculate the K constant of any spring according to the Hooke's law. Here, at first, we know we have three different forces: compressive, up to with different directions, tensile, and the shear to destroy something. We have two purposes. In this example, we'll try to do all of these to verify Hooke's law and to know how we can calculate the K constant of any spring. That's related with the work or what the capacity or what is this force can deal with how much newtons to can stretch specific number of centimeters or meter. Okay, that's with better words. Here, at first, this curve, this diagram, illustrate to us how the iron material or any from any kind of material with specific number of newtons will destroy to be two parts, but between the limit of the force to make this material bar be two parts, we have some flexibility. Without cross this limit, this shape will come back to the original shape. That's mean according to the flexibility or restoring force. Here to B at this curve, here we have two different relations. From 0 to A, it's approximately direct linear relationship, but after that, it's curves, it's not linear relation. Here, let me come back to the restoring force. If I crossed B, that's mean this material bar will goes to make some fractures until breaking stress and fracture point will be to two parts at plastic region. That's mean the elasticity or restoring force doesn't work anymore. Here, Hooke's law is F with any Newton equal minus KL, the K constant, and L, it's this extension. You can write E or L dash. Here, the minus, it's the opposite. It's assigned to the opposite direction of restoring force. We will work with mass, 100, 200, reach to 700 grams. How we can convert this mass to be force or weight with Newton unit. From this formula, F equal mg here, mass multiple gravitation. For example, let's calculate 1 Newton equal how much grams of mass. We know the force, it's 1 Newton. The gravitational force, we know its number. By that, the mass here will be approximately, we can say it's 100 grams. Here it's kilogram because Newton has another unit, kilogram multiple meter divided on second square. By that, we have here it's kilogram. In a gram, it's 102 something gram, approximately 100 gram. By that, 3 units, we can say it's equal approximately 300 grams, 5 in Newton, approximately 500 grams. Here, how we can how we could say K is equal the inverse of slope by using from Hooke's law F equal the K constant multiple extension. Let's calculate the K equal F divided on extension from slope from tan theta, slope or tan theta equal extension divided on force. By taking a look from equation 3 to 2, we had this form, K is equal the inverse of slope. Here we have this. Let me start from here, my solved example table. The original L was, let me say, 9 centimeters. Here we have masses, 200, 300, until 700 grams. That's mean the weight or the force will be 2, 3, until 7. The length of the spring, it's 10, the L2. L2 minus L1 equal the extension. By that, L2 12.3 minus the original L 9 centimeters. By that, the extension is 3.3. Okay, it goes like that. Theoretically side, to verify the Hooke's law, we will try to calculate K approximately directly. We will say K equal force with a Newton unit divided on extension with centimeter unit. Okay. Here, the first 2 points is irregular because the other are close from each other. According to this spring, it's approximately has K constant equal half a Newton to each centimeter. We need approximately, according to this cross area of the spring, it's the K equal half Newton to each centimeter. That means to make displacement to 1 centimeter, we need half Newton. Here, and after that, I take K average to minimize the mistakes as can as possible. Now let's go to the math to graphical side by using the slope, and let's take a look. The K constant from these each two different methods will be near or far from each other. At x-axis, I say each 2 centimeter is here equal 1 Newton. At y, each 2 centimeter equal 1 centimeter of extension. Here from the slope, it's equal 2.2 centimeter to divided on Newton. Here I have K constant, it's equal less than half a Newton. I need to make a displacement to 1 centimeter. Okay. The results, we can say it's near from each other. Dot 1, the difference between them approximately dot 1. Let's talk about the conclusion, the relation between extension and the weight or force is direct linear relation. The most of them, it's here. I need less than half Newton to make displacement to 1 centimeter, or 45 something Newton to extend the spring to 1 meter. That's it. Our lecture is finishes today. I'm sorry, I'm thirsting. Our lecture today is finished. It's Ramadan action. Today this video is finished. See you in next video.